Welcome back. So, today we are going to study two temporal characteristics, that is, two time characteristics um, that can be used to describe or summarize a random process. Now, in the last module, we have studied how to compute. We studied the grand view of a linear system where the random signal, that is the response of the linear system, is a member of a ensemble of random signals from a process y of t, and the input is also a random signal from the ensemble of random signals from y of x of t. Here, we last class itself we have shown you the operation. The convolution operation is used to determine the output of a linear time invariant system. How to calculate the response? The response is given by the convolution integral. It is a convolution between the input x of t and the unit impulse response of the system h of t. That is equal to the convolution integral. Now, today we are going to study some of the properties of the mean and the mean square of the response of such a system. Now, what will be the mean value of the output of a system? So that should be the expectation of y of t. Now, the expectation of y of t. Now, I can replace the y of t in. I can use the convolution integral to replace y of t. Now, that would be expectation of the integral, and y of t is replaced with x convolved with h of t, that is integral minus infinity to plus infinity of x of tau h of t minus tau d tau. So simply what I have done, I have replaced this y of t for the convolution integral in this expression. Now, this is true for all values of t. Simply we are not taking just one value of t and calculating the mean here. Here we are calculating the mean of the mean, or we calculating the average random signal. The average random signal here, that is for all the time points on the real axis. Okay, so here it is the expectation of y of t for all values of t, for each value of t. It is given by this expression here. Don't think that this is the expectation of one random variable. Here, this is the expectation of the random process, or we are trying to find out what is the average of the random process. Okay, now that is, this integral can be simplified by taking the expectation inside the integral. Now, here, what are the random variables? What are the fixed? What are the deterministic functions in this expression? Now, if you observe h, what is your h? H of t? H of t is a unit impulse response of the system. It is a characteristic of the system. It is a fixed function. It is a normal function. Okay, it is a fixed function. It is not a random variable or a random process. Now, that is why we have denoted that with normal lettering, whereas the random variable is the input variable, the variable that correspond to the input random signal, that is your small x. Small x is shown in bold letter. The small x is a random variable, so this expectation normally applies to the random variable, and h is a constant which is left outside. Okay, you have to remember this exercise. We have been doing this many times. This is This is a normal procedure how we do this. So h is a deterministic function, right? So we cannot apply the expectation to this one. Normally the constant comes outside the expectation. That's why we have written it outside this expression here. Now, okay, let me take the laser pointer. Now, uh, now this is the expectation of the random process. Normally we denote by using eta of t, right? Now, what happens if your random process is Whiteson stationary process? Then what will happen to the mean of the process? It is simply a constant, isn't it? So that eta of t is just replaced with a fixed constant eta x. Now the constant comes outside the integral and we are left with the integral of h of t minus tau t2. Now what will be this integral? This is another definite integral, and since we know what is the function h of t function, the integral of that function will give you another value which is another constant, okay, which I have denoted by using capital A. Now a constant times a constant will give you another constant. So in fact the mean of the response of the linear system is another constant if your system is, if your input is a Whiteson stationary process. If your input is a Whiteson stationary, then the output, then the mean of the response is also another constant value. Okay, that means this response will also have a constant mean. Okay, that is the implication here. Now consider the mean squared value of the system response. Can you recognize what would be the mean square value? Okay, anyway, okay, so normally this is sometimes also called as it is a y square. So y power 1 is called the first moment. When you have expectation of y square, it is called as the second moment. Okay, it is called second moment of the random process. But anyway, so this has got we have used this when we calculated the energy of the input process, right? The energy of the input process um, um, however, sorry, this is slightly different. Okay, slightly different. Sorry, it is the expectation of the second moment of y. Second moment, it is called second moment, moment, second moment of y, or it is simply the mean square value, mean square, or the mean of the square values of y of t. Okay, the mean of the square values of y of t. Now this applies for all the t on the time axis. So this is the expectation of the square of the random signal. Okay. Now similarly substituting for y of t is my response of the linear system. So hence it is given by the convolution integral, the following convolution integral. So for the first y of t, I will write y square of t, I will write that as y of t times y of t. For the first y of t, I will substitute this integral with respect to tau, variable tau 1, and for general purposes, for the second variable, I will substitute using this integral, because both of these are y of t and y of t. It is normally useful to take different dummy variables for each of these expressions. If you take both of them equal, then this expression collapses. It becomes a special case. For generality, normally we have to choose different dummy variables for each y of t. That is why I have taken this way. Now what will happen? So now I can take this integration inside and writing the expectation of the random variables. Here the random variables are concerning this x and this x. and these h's are constants, so these come normally outside the expectation. Now can you recognize what is the value, what is this expression here? Okay, what is this expression here? Okay, it is the expression of the product of two random variables of the same process x taken at times this time and this time at two different time points. So it is a definition of autocorrelation function. Now if your input signal, the input process is a Whiteson stationary process, then what will happen to the autocorrelation function? It is simply a function of the time difference between these two time points. The difference between these two time points, t minus tau 2 and t minus tau 1. Take the difference, it is t minus tau 1 minus of t plus tau 1. Therefore, it becomes tau 2 minus tau 1. Okay, tau 2 minus tau 1. Okay, tau 2 plus tau 1 actually. This is tau 2 plus tau 1. So there is a plus here. There's a slight mistake. That's okay. You can, as you can understand that. So it is simply, oh, so the difference of this one minus this one. So that would be tau 1 minus tau 2. So we got the same thing here. So only thing is, this has to be tau 1 minus tau 2. Okay. So the the mean square of the response is given as this integral here. It uses the autocorrelation function. Okay, it is a simple expression multiplied with the impulse response of the system. Okay, now thank you very much.